Hi, this is our video submission for the edition 2024 of the ML4Earth Hackathon. My name is Tanguy Frémont, and I worked on this project with Tom De Oliveira and Paul Martin. For this hackathon, we looked at the landcover.ai dataset. It's a total of 10,500 roughly images covering 215 square kilometers of rural areas across Poland. In the dataset, each image also has a corresponding mask. Every pixel of the mask is put into one of 5 categories: background, woodland, water, building, or road. And the masks put together essentially outline a sort of blend of the land usage of the area. Our goal for this hackathon was to design and train a foundation model on these data to try and be able to predict, given any image, the corresponding mask. So for this, the first step was data processing. We applied several transforms to normalize the pixel values. We also introduced variability in hue, brightness, contrast, saturation. We also apply a random horizontal flip, random cropping to the training data to try and augment it to make our model generalize better in the future. For the model itself, we chose to use the Swin transformer. We downloaded the weights pre-trained on an other aerial dataset, Sentinel-2, and we kept the first 5 layers frozen to retain the generalizable features learned from these pre-trained satellite images. We then integrated a feature pyramid network, where is it, right here, to improve multi-scale feature extraction. And then we added a segmentation hand at the end to process the feature maps from the feature pyramid network and output pixel-wise prediction for the different land cover classes. For training, since we plan to use a local GPU, we implemented a few strategies to make the most out of it while trying to maximize performance. We used the Atom optimizer, the reduce all-R on plateau learning rate scheduler, as well as cross entropy loss with class weighting and label smoothing to try to address class imbalance. As we'll see, the data set is pretty imbalanced. We also implemented early stopping. So for class imbalance, as you can see, the 5 classes are very, very imbalanced, as I was saying. More than 80% of images don't have any roads at all, and buildings is by far the most underrepresented class, with less than 2% of overall pixels representing a building. That's it. During our training, we monitored several key metrics, most notably IOU, accuracy, precision, recall, for both training and validation, and we did all that in TensorBoard. We also did a little bit of profiling, especially at the beginning, to make sure we weren't hitting compute bottlenecks. We included the resulting logs in the release page of the GitHub project. For the results in terms of performance, our model achieved a maximum IOU of 0.56 with a peak F1 score of 0.65. Validation accuracy reached 0.68 during the best training route, which consisted in 50 epochs, as you can see here. The model struggled a little bit more when it came to the, as I said earlier, rarer classes such as buildings and roads. But it still demonstrated strong capabilities, especially for distinguishing the most common classes. So background, forest, there's an example here, but water too. There are still potential improvements though. We think there are three main ways we could improve this. First, experimenting with more hyperparameters and configuration. Second, we should expand the dataset to include more roads and buildings, so maybe on a more urban area. And finally, since we had to reduce the images to 255 by 255, maybe training on larger images of 512 by 512 would help. And that's it for the presentation. Thank you for your time and attention.